And so let's start off. Last time, I want to repeat the last part of the lecture with you last on Wednesday, because I noticed that towards the end of the lecture, the things I was explaining wasn't showing on your end. So you didn't get it. You were just seeing my screen share. So I'd like to go back and add a little flesh to inversion recovery. Like I said last time, inversion recovery is not a pulse sequence that stands on its own, so to say. It can be applied to both spin echo, to both gradient echo, or whatever pulse sequence we want to use. Inversion recovery is a tool that is used to maximize a contrast between tissues that have similar T1 weighting differences. It could also be used to suppress some tissues we don't want their annoying signal to be in an image, or also suppressing them in the sense that it will also improve the contrast between that tissue being suppressed and the surrounding tissue. Like we were meant to know last time, inversion recovery is a step that starts with an application of an inverting pulse, so that the pulse inverts the horizontal magnetization. It notches down 180 degrees down. So after it's been knocked 180 degrees down, after the application of the 180 pulse, and the 180 pulse is removed, you now have growth, Z1 growth, longitudinal magnetization and growth. Nothing happens along the transverse plane, no magnetization at this moment at any point in time along the transverse plane. You only have magnetization along the transverse plane when you now apply a 90-degree pulse at any point in time. It could be at this point, it could be at this point, it could be, and so on and so forth. So whatever time we apply a 90-degree pulse, assuming we apply a 90-degree pulse here, we are going to have a particular amount of longitudinal magnetization. So at every point in time, we are going to have less amount of longitudinal magnetization that will be knocked down to form the transverse magnetization. So you are going to have a lesser signal when we are using inversion recovery. But we might want to ask why. In MRI, in fact, in all imaging procedures, we are interested in having a very good contrast, a very high contrast between tissues. So why would we want to have, why would we want to make do with a lesser signal, something that gives us a lesser signal? So why would we have to go through this process of knocking down the longitudinal magnetization towards in the opposite direction? At the end of the day, we have a lesser signal. There are so many we have so many reasons for that, which we are going to look at. Let's assume we have two tissues. that have similar rate of growth after application of a 90-degree pulse. A good example would be okay, gray matter and white matter. Gray matter of the brain and the white matter have very similar contrast and characteristics, very similar T1 relaxation. So if we use, of course, we've seen so many images of T1 with the contrast of the brain and T2 with the contrast of the brain. We could see that the gray matter and the white matter at times is they are very difficult, and not so difficult, but very at times difficult to distinguish. But their differences can be enhanced if we apply inversion recovery. So if we apply inversion recovery to that, at any point in time, we are going to have a greater contrast. Look at this. At any point in time, maybe at this point in time, this is the contrast we are going to get between these two. Contrast, 1, 2. Let's say we apply 90 degree here. We are going to get this amount of contrast and so on. Maybe here, this amount of contrast at this point. But if we now use an inversion recovery, we use inversion recovery, however we look at it, at any point, we're going to have, maybe at that same point, maybe at this same point, maybe we now apply a 90-degree pulse, we are going to have a greater contrast, between the white matter and the gray matter. So the inversion recovery helps us to enhance contrast. It helps in enhancement of contrast of a different tissue. So it's a very good tool in enhancing, especially when the contrast is based on T1 differences. So that is one use of inversion recovery. Another important use of inversion recovery is for this explanation I'm going to give now. We have parts. Can take this shape and have CFS, spinal fluid, taking this shape. At every point in time, whereas you can have both white matter and gray matter, any point in between them. This is for part. This is cerebrospinal fluid. One of these is a white matter. One is a white matter, one is a gray matter. So at this point, we have different points at which they cross the MX axis. That is the transverse plane. At this point, this is the null point for parts. If you apply a 90-degree pulse here, there won't be any contribution due to that of parts. So this is the null point for parts. For either the white matter or the gray matter, there are null points at this point. Then for CFS, we're going to have a null point here. Of course, we know that the fluid is mainly composed of water, so we can take the null point of water to the closely along this point. So this is a null point for CFS. And the distance from here, and this is our time axis. The distance from here to here is time of inversion. Inversion. So the time of inversion is the time it takes for any particular tissue to be inverted to cross the to have zero longitudinal magnetization. The time for any tissue to have zero longitudinal magnetization. So at that point, if we can calculate the TI of any tissue and we apply a 90-degree pulse at that point, there won't be any contribution of that tissue in that image. So the tissue will be highly suppressed. So in that case, we say that tissue has been suppressed. If it is fat, let's say the null point of fat occurs at maybe 20 milliseconds. 20 milliseconds. It therefore means that if we apply a 90-degree pulse after time 20 milliseconds, there won't be any contribution to that coming from fat. If you apply at, maybe this one gives us 250 milliseconds at this point, the CFS will now be suppressed so that we now have CFS and suppressed image. At this point, where fat is suppressed, if you take an image at this point, where we want to suppress fat, we normally call that steer image. Short brow inversion recovery. Whenever we see on an MRI image this sequence or this term, we are talking about the fat being suppressed because it has a short inversion recovery time. Whereas if you have for this is our common flare, which is available. Of course, these two are available on all MRI scanners. So this is a fluid attenuated inversion recovery because the fluid and content, of course, is mainly water. So if we now null it, if we now apply the 90-degree at this end, we are going to have a flare image. And this is all. This is about all there is to inversion recovery. All we need to know about inversion recovery is it is a tool that is used to enhance contrast. Basically, I'm used to enhance contrast because at times we can have some annoying signal from some of these tissues. I think we are looking at we are looking at the brain tissue, and we don't have and we don't want we don't want contribution, so much contribution from fat. Just null it. Just null it and then have a better, better contrast among the various tissues of interest. Likewise, fluid. So I want to look at. I'm going to have some screenshots of a kind of a summary of the pulse sequences we've been talking about. All this why? Because this is the major area where MRI is so versatile. Because MRI is not like a CT, which competes with it in terms of tissue contrast, contrast. A tissue has so many limitations in terms of how we manage our contrast, but MRI has almost unlimited possibility of contrast management because based on this, the parameters of TE, TR, and also flip angle, you can so modify an image so that it is can be T1 weighted, T2 weighted, T2 star weighted, and even it can be flare T2 weighted, it can be flare T1 weighted, and be flare and so on and so forth. So I want to look at some of these images, look at their differences, maybe also look at some of the advantages of using one over the other, and just have a good feel of this imaging sequence. So let me share my screen. Can you see the screen?
Yes, we can see.
Let's see if I can go to slideshow. So I want to look at gradient. We have two images from the same specimen from the same patient. One was acquired using a gradient echo, and the other one was acquired using a spin echo. Can we differentiate which is the spin and which is the gradient echo? And somebody just help us distinguish. Is the first or which is the first? Is the first a spin echo, a sequence, or a gradient echo sequence?
Sir,
Yeah, I can hear you. I'll speak on.
I don't know which one is the first, but on the screen, maybe to the left.
Okay. To the left.
Right, the one to the right is a gradient echo.
Okay, that's excellent. You shouldn't give us any problem. You can see the gradient echo versus spin echo. The spin echo, you can see the.
Hello, sir.
Yes.
Chief Akindele.
Please.
Hello, sir.
Hello, I can hear you.
Sir, which one is the spin echo?
The one to the left on the screen.
And the one to
left on the screen. Can
okay.
Can you use your cursor?
Yeah, can you see the cursor?
Okay, that one, Abi.
Yeah, that's the spin echo.
Oh, okay.
And this one here is the gradient echo. You can see this one is
Okay.
grainier. This one is noisier. The one here is noisier than this. So the SNR, the signal to noise ratio of this is higher. Why is it so? In a gradient echo, because we don't use the 180 refocusing and pulse. So this image is subject to not inhomogeneity and the magnetic susceptibility of different tissues. Of course, the protons in different tissues. You are going to have not so wonderful contrast. So it depends on, of course, the what we want to look at. It is not something that requires so much contrast between the bone and the tissues surrounding it. Then we might make do with the gradient echo, because of course it is faster. Okay, well, both are T1 weighted. Anyway, got to get to see that again. Then in the gradient echo, a flip angle is about the most important discriminating factor. Ability to be able to get the right flip angle for any application is key to understanding gradient echo, because a particular spin angle, a particular flip angle, maybe 90-degree, will be different. Image we capture with a particular flip angle of 90-degree will be different from that which is captured with 2-degree, 5-degree, and so on and so forth. So this equation, the nth angle is just the arctan of the exponent, the negative exponent of the ratio of the repetition time over T1. So the nth angle gives us the largest signal for a given TR and T1. So for a given TR, for a given nth angle, we are going to have some combination of T1 and TR. What do you mean? Let's go to the next slide. I look at the GRE and the nth angle acquired. The graph was drawn with different flip angles from about 5 to around 80 something. This is the curve for that we got with part. That is, we look at a particular part tissue, and we began to vary the flip angle based on some combinations of TR and T1. At the end of the day, we got this curve. And for muscle, we have this. So if we want to maximize contrast between part and muscle, we look at the area in which we are going to have the greatest contrast. Of course, this is the difference between the MRI signal of part and the muscle. So for example here, at this point, the difference between the MRI signal here and here will give us something close to this. So just draw a vertical line here. The difference between that, we get the plot we put down here. At this point, they are about 0, no difference. So if we take a flip angle of less than 10 degrees, we are not going to have any contrast. The contrast will automatically be 0. So you can see we have for parts, for you to have a maximum contrast, for muscle, the nth angle should be around 10 degrees, 12, 10 degrees. While for part, nth angle is approximately close to 20 degrees. So but the maximum contrast will be when we apply an nth angle to a patient around 20 degrees. And again, we should understand that the nth angle is directly proportional, yes, the nth angle is directly proportional to the field strength. We have, if you have our own 0.3 Tesla machine, the flip angle, the nth angle for parts will be different for that of a 1 Tesla, 1.5 Tesla machine and the 3.0 Tesla machine. So it's a great deal of work. Of course, the manufacturers have already done that for us, but at times it's also good for us to check things out ourselves. So for this, if you want to have the maximum signal between the part and muscle, we should apply a flip angle of about 20 degrees, so that we have this maximum amount. But if we begin to increase the flip angle, we see at some point in time, the contrast between them begins to decrease. But this one will have sharp rise in contrast, or we have a gradual drop as the angle increases. So we now look at this is a musculoskeletal image of musculoskeletal image acquired at different flip angles. We have 1 degree, 5, 10, 20, 30, 45, 60, and 90. At 1 degree, you can see this is between the fat and the muscle. We want to look at the contrast between fat and muscle. At 1 degree, we could see that the contrast is almost 0, which is evident from a graph here. At 1 degree here, you can see the contrast is about 0, close to 0. When we now increase it to 5 degrees, we now begin to have a contrast between this fat here between this fat here and this muscle here, between this fat and this muscle. As the amount of angle begins to increase, we now begin to have increased contrast. But at 10 degrees, we now have high muscle signal. Look at our muscle. The signal becomes high. How is it high? It is high when the signal is whitish. When we have a white signal, it means, or white signal compared to other signals. If it is this one is whiter, you can see this muscle part here is whiter than this, 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 and whiter than this. So at this point, we have the highest amount of signal due to coming from the muscle. Of course, it is evident from that. For muscle, ends angle for muscle is around 10 degrees. So for that, we're going to have the highest signal coming from fat, from muscle. Then for fat, as we got to 20 degrees, I see a shift of focus of signal intensity from muscle to fat. Now have high fat signal here. It's a high fat signal. Signal is whiter, is about very white here. So very high fat signal. But when we increase it to 30 degrees, this is where we have our highest contrast. Let's look at the diagram again. Well, this is not clearly evident, but anyway, this is more than 20 degrees. So for 30 degrees, since we didn't acquire with 25 degrees, we didn't acquire with 25 degrees. So from that image, 30 degrees seems to be, it's about the highest from the combinations of flip angles we have there. So we now have highest contrast between fat and muscle. You can see the fat and muscle. This one is darker than this. So we have highest contrast between the two tissues. So the S angle is used to discriminate between contrast. It is used to help modify contrast between tissues. So a very good understanding of that will help us, will be key us to be able to diagnose any pathology around between fat and between fat and muscle. So that goes on and on. Though we still have some appreciable contrast in all these other two, but the greatest amount of contrast is about here. Of course, this is the worst. 1 degree. We look at 2 images acquired with T1 and T2 sequences. T1 and T2 sequences, they are actually You can call them real pulse sequence. You can have a gradient echo that is T1 weighted, the gradient echo that is T2 weighted, a flag image that is T1 weighted or T2 weighted, a spin echo that is T1 weighted or T2 image. But as the case may be, they have their subtool differences. Have T1 here and T2 here, because this is an axial image of the brain. We look at these are T1. These are T1 image, and like we know, T1 is mostly governed by time of repetition. T1 is governed by time of repetition, whereas T2 is governed by time of echo. Time of echo. We look at this T1 here, T1 contrast. We look at, we have, let's assume this is white matter. Like I said before, for T1, we look at the T1 regrowth curve. The T1 curve here towards the right-hand side of this down image. We look at the curve for CSF. We look at the curve for both white and gray matter because they have similar T1 decay scheme. Oh, yeah, this goes. If we apply, if we wait an appreciable, if we wait for a very short while before we take our image, if we wait for a short T1, a short T1, or a short TR, we are going to have this thing. Okay. These are TR time. If you take the image at this point, or if you sample the image at this point, and see the T1 not so pronounced, but for some long, not so pronounced, but and something increasing. But for a very long TR, the contrast will be reduced. So if you wait for a sufficiently long period of time, there won't be contrast due to T1 any longer. So most T1 images, they are captured with not so much longer a TR, but a shorter TR for you to have T1 weighted image. Then for T2 weighted image, because at this point, the time of echo between them is small. So as the longitudinal signal begins to fall into the transverse plane, it begins to fall into the transverse plane. We have an enhancement of weighting due to this also. Begin to have an enhancement of contrast due to T2. So if you wait for a sufficient amount of time, you're going to have a better T2 differences. So this T2 difference will be enhanced with larger TE. The diagram is not so explanatory. I think we have. So MR image and contrast. We want to look at T1 and T2. They are basically, if you have short T2, for T2 weighted image, long T2 will give us a high signal. Long T2 is going to give us a high signal, as you saw in this image, in the other image. Then for T1 weighted image, if you have a tissue with a very, very short T1, we are going to have a high signal from that. So that one is going to appear white. While for T2 image, if you have a tissue with a very long T2, that tissue is going to have a white background. I think we have less than a minute. Let me stop. Let me stop for now.
Hello?
And hello.
Yes, sir. Sorry, before you go, sir, under the T1 weighted image, I guess that long T2, it should be T1, Abi.
Yeah, wait. Let me. I don't want this
Should be
thing
a
to
mistake.
end.
Okay.
Let me stop this share again.